Hi everyone, we are moving on to 3.5, part 2. So same section, just a little bit more of it. We're going to start the first problem by graphing in slope-intercept form. So remember that slope-intercept form is y is equal to mx plus b. Right now, y is not alone. So our first step into getting this equation into that form is to get y alone and subtract 2x from both sides. So then you will have y is equal to negative 2x plus 2. Notice I wrote the x term first because that's how it is in slope-intercept form. Then identify your slope. So our slope here is negative 2. It's the number in front of x. And our y-intercept, b, is equal to 2. So I go ahead and I plot those values. So b is my y-intercept, 0, 2. That's where you begin your graph on the y-axis. And I use my slope of negative 2 or negative 2 over 1 in order to see the rise over run. That means I'm going down 2, right 1, down 2, right 1, or up 2, left 1, and then I connect. Whoa, that was not a line. My points. And there's my graphed equation of a line. Identify the x-intercept. For the x-intercept, we can use the same process we did for finding x and y-intercepts by plugging 0 in for your y. But because we graphed it already, we can just look on the x-axis. On the x-axis, our line touches the point 1, 0. And that is the x-intercept of this line. Okay. All right, next problem. A linear function g models the relationship in which the dependent variable increases by 3 units. For every 1 unit, the independent variable increases. Graph g when g of 0 is 3. Identify the slope, identify the y-intercept, and the x-intercept of the graph. So the first step here is to look at the keywords dependent variable increases by 3. That means that our y, because y is dependent variable, is increasing by 3, and our x is increasing as well by 1, because that's the independent variable. So it's telling you the change in y over the change in x. And we use a triangle to represent change in the variables. You don't have to write this part, but it kind of tells me how to translate this statement. Since the change in y is increasing by 3, my slope is positive 3 over, for every 1 unit, the independent variable decreases, so all over 1. Now, because they both say increases, both values are positive. So you can also write this as m is equal to 3. They give you a point here. Remember that the number inside the parentheses of a function is your x, and what it equals is your y. So this point I can just rewrite as 0, 3. Notice it's 0, a number, and that automatically tells us what our y-intercept is. Because a y-intercept is on the y-axis where x is 0, or 0, a number. Let's continue the problem by graphing and then locating our x-intercept. If you want to graph this, please pause the video and then check your answer. There's your graph. Once you graph this problem, you can look on your x-axis for the x-intercept. And notice it's negative 1, 0. And that's it for this problem. If you wanted to write the equation for this function, we can use function notation, g of x is equal to, and now it's just using that regular equation of a line, slope-intercept form to write it out. We have our slope as 3x plus our y-intercept, which is also 3. And that's our function. All right, here are your next few problems. It says graph the linear equation and identify the x-intercepts. So what I would like you guys to do is pause this video, make sure every equation has y alone, because we want it in slope-intercept form, which looks like this. And then identify what your slope is and your y-intercept is. You can start graphing it on your own as well, or just play the video and watch me graph it with you. Okay, so here are all of your equations, your slopes, and your y-intercepts. I'm going to graph with you guys. Notice, remember, for 10 and 11, you actually had to do some work to get y alone. In number 11, you might have gotten negative x over 2, and it looked like this. Just make sure you separate the number from your variable so you can see your slope nicely. Okay, so for the first one, you begin your graph at negative 4, and our slope is 4, or 4 over 1. Up, 1, 2, 3, 4, right 1. Up, 1, 2, 3, 4, right 1. I can go in the opposite direction, but I don't have room. Okay. The slope was positive, and therefore it's increasing from left to right. And number 10, our y-intercept begins at negative 3. And our slope is down 3, right 1, or up 3, left 1, because we don't have space. Okay, go ahead and connect, and you should have arrows. In the last one, your graph begins at 3. Our slope is negative 1/2, so down 2, down 1, right 2, down 1, right 2, or up 1, left 2. And connect. Okay, so notice in number 1, our x-intercept is nicely found. It's at 1, 0. In number 10, our x-intercept's at negative 1, 0. And in number 11, it's a little difficult to see unless I were to continue that arrow down here and estimate where it hits. But instead of estimating, we know we have the tools to do it algebraically. So I'm going to use the standard form equation, and to find the x-intercept, I'm plugging 0 in for y. So it becomes x plus 2 times 0 equals 6. 2 times 0 cancels, and I'll get x is equal to 6. And therefore my x-intercept is 6, 0. Okay. And on to number 12. A linear function h models a relationship in which the dependent variable decreases by 2. You're thinking negative, positive here. And that's for every 5 units that the independent variable increases, positive. So graph h when h of 0 is 4. Identify the slope. Identify the y-intercept. And I'm going to say again, use your graph to find the x-intercept. Try this problem on your own, because we just recently did one similar, and then we'll go over it together. All right, guys, so these are the slope and y-intercepts you should have gotten in the beginning of the problem. 0, 4 for the y, and negative 2 over 5 for the slope. We have a negative 2 in this case because the dependent variable decreases by 2. Now, I'm going to write the equation out without function notation in order to find the x-intercept. So y equals the slope x plus the y-intercept 4. And then I want you guys to graph it, and your graph ends up looking like this. Now, the reason I did that is because to find the x-intercept, I wanted you guys to look at the x-axis and see where the line crosses. But it does not cross if you have a very small graph like mine. Therefore, if your graph was as tiny as mine where you couldn't see where the line would touch the x-axis, you can do it algebraically just like we've done in previous x-intercept, y-intercept problems. So what I'm going to do is I'm plugging 0 in for y and solving for x. When you solve for x here, you're going to get that x is equal to 10. So once you have x equals 10, we know the x-intercept is 10, 0. Okay, so there's now we have our y-intercept, our x-intercept, the slope, and let's go ahead and graph it just to visualize it and rewrite it in the function notation they want because it says h. So back to my graph, h of x is equal to negative 2/5 x plus 4. Oops. So when I graph it, I start at 0, 4. I go down 2, right 4. And like I said, it didn't fit to keep going on my graph. It might on yours. And we want to use the symbol that they use for the function. And I think that is it. All right, guys, last problem. A submersible that is exploring the ocean floor begins to ascend, meaning going up to the ocean floor surface, and the elevation h in feet of the submersible is modeled by the function that's written, where t is time measured in minutes since the submersible began to ascend. So you have the submersible in the ocean moving up to the surface of the ocean floor. So we're going to have to graph this function, identify the domain, identify the range, interpret in the meaning of the problem, context of the problem, the slope and the intercepts. So my suggestion for you is to graph this function using the intercepts. The reason I say that is because if you look at the slope right now, which we're going to have to identify, it's 650. Meaning 650 over 1, and we're probably going to have to scale this graph, so it will be difficult to count your rise over run going up and to the right or down and to the left. So my suggestion is to start by finding your intercepts and graphing using those 2 points. So I'm just going to make a little bit of space here, and I'm going to do part A by setting up my table and graphing my x and y intercepts. Remember, y-intercept is when you plug in 0 for x, and x-intercept is plugging 0 in for y. So when I plug 0 in for x, I'm going to change my function h of t. I'm going to put a y there to make it easier. And remember that the variable t represents your input x, so I'm going to plug 0 in for that variable, minus 1300. 0 times a number will cancel to be 0, and we're left with y equals negative 1300. Okay. Step 2, finding the x-intercept. This means we're going to plug 0 in for the y, or the h of t. So I'm going to plug 0 in for my y, and I'm going to solve for my t, or my x value. So my first step to solving for t here is to add 1300 to both sides of the equation. And I'm left with 1300 equals 650 t. Divide both sides by 650, and we get that t is equal to 2. Now that I have 2 points, I don't need to use my slope to graph, I just need to connect those 2 points. All right, when I graph this function, I know that this submersible is going to start at negative height because it's underneath the ocean level. So if you're underneath the surface of the ocean, we consider that height to be negative, versus when you're on the surface, it's 0, and when you're above, it would be positive numbers. The submersible will never be flying in the air, it's just going to hit ocean level. It's going to stop at 0. So when I draw my graph, I know that my y values are going to mostly be negative for the entire graph until it hits the ocean floor. So I'm going to focus on the lower half, whoopsies, of my graph so that I have negative y values and our positive x values. Remember, the x in this problem is t, and our y was h of t. So time can only be positive, and that's why I'm on the right side of my quadrant. If I continued it, you can see where the values go. So my x's can go up by 1 per minute, but my y's are up to 1,300, so I need to go up by thousands here, or maybe if you have more space, by 500. So 1,000, 2,000, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to make more space. 13. Okay? And that's our starting point right there, because our y-intercept was 0, 1,300. Our x-intercept, if we go back, was 2, 0. So my x-intercept over here is on the x-axis, and then I connect those 2 points. And I would actually be careful here. I made a mistake. I shouldn't go past these 2 points, because if I did, I'd be saying that my submersible is flying above the ocean. It stops at 0. It should stop at 0. And I can't go past here because that's negative time, and we can't go back in time. So this here represents the submersible going up, ascending to the ocean level, and stopping. So now let's start interpreting some of these questions. Let's find the domain and the range first. Remember that our domain is all possible x's. So we know that x starts at time t equaling 0, and it goes up to time t equaling 2. So our x's fall between the time being 0 minutes to the time being 2 minutes. 2 minutes is where we hit the surface of the ocean. The range is all the possible y values. So what does y fall between? Well, we know that it starts at negative 1,300 feet. I'm saying 1,300, I'm sorry guys, it's 13,000, negative 13,000 feet. And it's going up and ascending to the ocean surface, which is at 0 feet. So I know that my range falls between negative 13,000 and 0 feet. Now the second part of the problem says interpret the slope and the intercepts of the graph. So I'm going to erase all of this, make sure you have it down. We're going to do each one separately. So we know our slope is the number in front of x, which is 650, or 650 over 1. What that means, that's our rate. That's how fast this submersible is going up or ascending. It's going up 600 feet per every 1 minute, because we're talking about t equaling time in minutes. And we'll write the word ascending. Our x-intercept was 2, 0. At time t equaling 2, at 2 minutes, our submersible is at 0 feet. So we can say the submersible reaches the ocean's surface. And lastly is our y-intercept, which is at 0, negative 13,000. And that's telling us that at time t equaling 0, at the starting time, the submersible is 13,000 feet below the surface of the ocean. So let me zoom out. And we can say starts. You can say 13,000 below surface, or at negative 13,000 feet. Okay, so That was a little tough to kind of visualize and understand, but if you're able to follow along, that's awesome. If you have any questions, make sure you write them down. That's the end of part 2. I would like you to try this on your own, and we're going to go over it as a warm-up in class next time. So it's very similar to what we just did.